Hello, I'm James Wootton, and I do things with quantum computers. Today, I'm going to do something for no particular reason, something that isn't really sensible at all, but I'm going to do it anyway. And that is to take a game and then to store it on a quantum computer, kind of, and then take it off the quantum computer again, and then play the game. I could play the game without going through this convoluted quantum thing, but I'm going to go through a convoluted quantum thing because I can. The inspiration for this was an LGR video, which I watched yesterday, and I'll put a link in the description below. He takes a game, records it onto some tape, on a nice reel-to-reel tape thingy, and then takes it off again and plays it. Why? Because he could. And that's basically why I'm doing this with a quantum computer. Except, of course, that tape was intended to be a data storage medium, and putting games on tape kind of that was intended for audio is not a weird thing. I used to do that when I was a kid. I used to have games for my Amstrad CPC 464 that were on cassettes. So the thing that LGR did was extremely sensible in comparison to what I'm doing, which is to put it on a quantum computer. But nevertheless, let's do it. So I'm not going to sort of live code this. I've already got a Jupyter notebook set up, partly because I already tried to record this video once, and it turned out the microphone wasn't plugged in properly. Great. Anyway, let's get on with it. So I'm using Qiskit, which is a framework for quantum computing, blah, blah, blah. I work on this as part of my work, so it's very tempting to go into sort of advertising mode. This video was brought to you by some idiot's stupid idea. It is not brought to you by Qiskit. But I am going to use Qiskit, and what I'm going to need is Quantum Circuit, which is quantum circuits are the basic component of any quantum program, so we're going to need those. Assemble is how we take a quantum program and put it into a form that can be actually run by a quantum computer, or at least it's the way Qiskit does it. And both AIR and IBM Q are ways that we get backends. Backends is what Qiskit uses to refer to things that can actually run quantum programs. Okay, so we have to actually run this code cell. And then we have to load our IBM Q account if we're going to use a real quantum computer. There are some publicly available ones, and there are some bigger and fancier ones that are not publicly available. As an IBM employee, I have access to some of those bigger, fancier ones, and I'm going to completely abuse that privilege today. I'm using one. I'm sure they won't mind. I mean, they knew when they hired me that I do this sort of stupid stuff. So. Okay, so I've loaded my account. That's especially easy in the IBM Quantum Lab. No, this is not brought to you by IBM. Don't go into advert mode. I'm going to set up a simulator using AIR, so that I just say AIR, give me a backend, and the backend I want is the QASM simulator, which is just a simulator which acts like a quantum computer would. I am also going to use Mumbai. So you do ibmq.providers to get a list of the providers available to you. Different providers have different devices that they can actually offer you. Now the last in this list is the one that gives me the access that I need. So I'm using that one, and I say get backend, and I ask for ibmq underscore Mumbai, and I'm using Mumbai because it has the best compromise between size and busyness. I checked it out. It's not very busy today. Other devices, very busy. I'm not going to use those because I'll just be in a queue. So I'm going to use Mumbai instead. Okay, so run that. And let's see how many qubits it has. So I do Mumbai.properties to get some properties of it. And the particular property I'm after is the number of qubits, or the qubits. So I hit the len of this list of qubits to see how many qubits it has. It has 27. I knew that already. I don't know why I needed to add that little aside. You know, I do know things. Okay, so let's set up a quantum circuit. We're going to set up a quantum circuit with these 27 qubits, and I've used n to hold this number. And then we do things to those qubits, and then we take a look at them. So let's actually comment this out. How do I do comments again on this keyboard? Not like that. Anyway. Okay, let's get rid of them like that. So I can run this with nothing in the circuit. We just create the circuit and then we do measurement. This takes the set of quantum bits and just turns it into a normal bit string so we can actually look at it. And we find that if we do nothing in the circuit, we just get all of those 27 bits in the bit string to be 0. And if we were to do something such as this X operation on qubit 2, what we would find is that it acts essentially as a NOT gate, which flips one of those bits from 0 to 1. The qubits are indexed from 0 and also numbered from right to left. So this is qubit 0, or the bit associated with qubit 0. This is the bit onto which we write the output for qubit 1. And this is the bit on which we write the output for qubit 2, which is why it's the one that got flipped. Now, the other bit that was in here is a small rotation, and I'm using this to be a very simple emulation of the effect of noise, because noise in a real quantum system means that we don't just get the result that we should do, we get other results as well that are slightly perturbed. So, I should have also noted that we are repeating this many times. So we're repeating it 8,192 times because that is the maximum number of times we can repeat it. And before, when it was perfect, all of those were coming out the same answer. This time, most of them are coming out with the answer it should be, but we're also getting some random stuff that is not that. So when we are going to be using a real quantum computer, we're going to have to mitigate the effects of this sort of nonsense. Okay, so we want to store a bit string in a quantum computer, and that bit string should correspond to a game. That is our eventual goal. Now, any game has at least thousands of characters in its source code. Each of those characters can be encoded in a byte, which is 8 bits. So we're looking at sort of 10,000 bits at least, and we've got a 27 qubit quantum computer. So there's a big difference between 27 and like 10,000. So how are we going to deal with this? Well, we can just split our bit string up into 27-bit chunks and make a circuit for each of those and then just have it encoded in many circuits. So we're never really going to have the whole game on one quantum computer at once. But this whole thing is nonsense anyway, so who cares? It just has to go through the quantum computer just to be needlessly fancy. That is the whole point. What we're doing here, if what we're doing here can be said to have a point. So let's have an example of a bit string that is too big to be fit on a single quantum computer, but not too big to fit on the screen. So we're doing a 100-bit bit string. I've just generated that randomly. There's a 100-bit bit string. And then I'm going to use this little line to split that up into chunks that are only n bits long. So here's the first 27 bits of that big bit string, and then here's the next 27, and the next, and then here's the rest. Then I'm going to create a list of circuits, and I'm going to go through all of these little bit strings. So when I iterate through this bits and split bits, it's going to go through all of these bit strings in this list split bits. So this is going to be the first bits, and this is going to be the next bits, and so on and so forth. And then I'm going to loop through all of the bits in each of these. So when I'm looping through, so when this is our bits, I will loop through these bit strings. It will first be 1, and then it will be another 1, and so on and so forth. And if that bit is 1, I'm going to do this X operation in the quantum circuit in order to flip the default value of 0 to a 1. Now, the reason why I'm not doing this on, so this is, this Q is the address of the bit. So the first one is going to be 0 here, and then that one's going to be 1 and 2 and so forth. But Qiskit actually likes to number things from the right, so 0, 1, and 2, and so forth. So it's just to convert between left and right, we take the total length of this string, because we've used the length of each of these little bit strings as the number of qubits that we need in this particular circuit. We take that number and we do that number -1 minus this index, just to switch it all over. Okay, I remember doing this in the first take as well. That's obviously a classic move that has to be in this video. Then we measure everything, and that's the circuit we need. We append it to our list of circuits in order to use it later on. Okay, run that. And now we choose how many shots we want to do. We assemble the quads, this time for the whole list of circuits rather than just one circuit. And then we can run it on a simulator. And if we do that, then we can take a look at all of the results. So we can run through each of these circuits. And if we, okay, so this gave us a job result when we ran it. And this just includes all of the information about the job we sent. When we actually want to get the result, then we do job.result to get the result object. So it's the counts that we're actually interested in, which are the bit strings and how many times each of those bit strings occurred. And so we see that for the first circuit, we got this bit string all the time. And this bit string is hopefully exactly the bit string that should be encoded there. And then we got this bit string all the time for the second circuit, which should be exactly this. And so if we included a rotation in here, then we would also have a little effect of noise, so we can see what that would look like. So let's put a little rotation angle, and let's apply this to exactly the same qubit as we had before. And then we run that. We run that, and then we run this, and then we look at what the results are. And then we should see the slightly perturbed version of these results. And this is taking a bit longer because it has more different kind of results going on here. So we see again that one is very dominant, and that's probably the one that we're supposed to have. But we also get all of these bits of nonsense that we're going to have to mitigate for. Yeah, so this is the kind of thing that we see from a real device. They are prototype devices. They don't currently have error correction. This is getting a bit educational now. Let's roll back a bit. This is supposed to be nonsense. Okay, when we want to actually extract our output, so what is our output supposed to be? Well, this was our input, and all we were supposed to do is put this on a quantum computer and then take it off again. So the output should be exactly the same as the input. What we're going to do is go through all of our circuits. We are going to take these counts results, so the bit strings and how many times they occurred, and then we're going to, for each bit in the bit strings, calculate the probability based on these results that we get a 0 or a 1 for that particular bit. And so we should have, each of these are actually certain. For a particular bit, it's either supposed to be 0, so its probability of being a 0 should be 1. It should be certain to be a 0. And then we're going to have bits that are 1, so they should be certain to be a 1. But because of this noise, we're going to see something a little bit different. So maybe we'll have some pretty certain to be a 0, and we will just assume that they are zeros. And we're going to have some that are pretty certain to be 1s, and we're going to assume that they are 1s. So that's how we're going to decode this. It's far simpler than real error mitigation or error correction that we have to do in real quantum computers. But as I said, this is straying into educational territory now, so let's get back to being nonsense. So we just iterate for all of the strings in these count dictionaries. So that, for example, goes through this one and looks at how many times that happened. And we go through this one and look at how many times that happened. We look at all of the bit values in here, and we use all of that information in this whole bit to calculate what the probability is of the 0 or 1 for that particular circuit and for the results of that. And then we go through all of those probabilities. And if we find that the probability of getting a 1 is less than half, so it's more likely to be a 0, then we add a 0 to our corrected string. And otherwise, we put a 1. And then we compile those all together to get our output bits. So let's run that and see what happens. And we get a bit string. So that's at least what should happen. And now let's see if it's the same as what it should be. Yes, the statement that they are the same is true. So great. Now I've basically compiled all of that into a function. So this bits to quantum does all of the stuff from taking the input bit string that we provide and outputting the circuits that we use to encode that and the job object that corresponds to us just sending it off to a device. And the number of bits it uses to encode. So when we break it up into chunks, the length of each of these chunks, we look at the number of qubits in a device and we use that for whatever backend we have asked to do this on. And this actually won't work if you do it on a simulator now, but the way I've created this function really assumes you're going to use it on a device. Otherwise, it's exactly the same as before. So let's just execute that. And then the rest of it, which is where we are taking the results out of the job object and compiling them into the output bit string. That's all going to be in this function quantum to bits, which takes our circuits and our job object and outputs the output bits. So let's execute that. And then we can get to the actual point where we have our input bits, we run them on a device, and we extract our output bits. So I'm not going to run that because then I'll get in the queue and well, actually I want to run something else a bit later rather than this stupid random bit string that we just created. Okay, so I'll ignore all of that. What I actually want to encode is this set of text. It is a C program which runs a simple implementation of chess. So this is a game, and it's a game that's expressible in about 8,000 bits. So it's a very minimal example of chess. You can see who did it here, Oscar Toledo. I really should have looked up the pronunciation before I did this video, or pronunciation, but it's totally his thing, not mine. So check out his website if you want to know more about his quest to make one of the most efficient implementations of the chess game. And there are other people who have done similar things as well. There's an old game for the ZX Spectrum that has a similar number of bits, but that's not the one I did. So I'm going to go over to this website and just run the C code to show you that it is indeed a game. So here is the board on which chess is happening. The P's are pawns, the R's are rooks, and if we press enter, you'll see a game being implemented in front of our eyes. So this is the game that I'm going to encode and then get off the quantum computer. This game is going to go via a quantum computer. For this, I need to turn the text into bits. So for that, there are ways of turning text into numbers via normal encodings that are used for all kinds of things. Then you can turn those numbers into binary. So this is something that's moderately straightforward to do. I wrote a couple of functions that do that. They take text and turn it into bits. They take bits and turn it into text. But let's not meditate too long upon my happy code. So for example, let's turn hello world into bits. There you go. And then let's turn it back into hello world. It works. Well, at least for hello world. So now we have the ability to turn this chess program into a bit string, and then we can send this bit string off to the Mumbai device and run it. So by running these two things, I am sending this game via a quantum computer. So let's run it. Let's go. No, it isn't. I completely forgot to actually define what this Toledo chess was. I forgot to run this code cell, which is the kind of problem you can have in Jupyter Notebook sometimes. So Now we get the magical moment where it's just sent a game to be squeezed through a quantum computer, a prototype version of one of the most advanced pieces of technology in the world. One of the coldest points in the universe is the chip that is going to run this, because it's in a dilution refrigerator being kept at millikelvin in order to protect the quantum phenomena that are being used here. I'm trying to make it sound all dramatic, but it is just kind of noisy. So here is the job. As you can see here, I use Mumbai a lot because it's often the one that has the least view. It was created at this time, March the 14th. It's Pi Day, which is not really related to the fact that I'm putting a game through a quantum computer, but we needed to know the value of pi in order to make a quantum computer. I'm pretty sure that statement must be true. It's currently transpiling, and then it's validating. Hang on a minute. That's not this job. That's the job I did earlier when I did the version of the mic wasn't. It's still Pi Day. Oh, it's almost Pi time on Pi Day. Maybe I did this 4 minutes later. Although that is just as irrelevant as anything else that we're doing here, so nevertheless. It validated in 3.7 seconds. It was in the queue for 3.4 seconds. Wow. There really wasn't much of a queue for Mumbai today. I hit it at the sweet spot. And now it's running. And it will take probably about 15 minutes to run the many circuits that are being run in order to take that huge number of bits and squeeze them through a quantum computer. So now I have some time to kill. Back on the old Amstrad CPC 464, when I used to load things off cassette tapes, that used to take a while. And what I used to do at that time was read a Beano. So why not do the same thing? Tiny top hats for cats. That's a good idea. It's run. So let us check out the result. Although before we do that, you didn't get any cool reel-to-reel recordings like in LGR's video. So let's look at some pictures. There is a chip, such as the one that we ran this on. Although that's a hummingbird, we ran it on a Falcon. Here's a 5-qubit device. You can see the superconducting circuits that we encoded this game into for no particular reason. Here's a dilution refrigerator used to make this one of the coldest places of the universe. Here is an idiot with a microphone. And now let's go back to our program. So this is what we just ran. We turned these bits into circuits and a job object that sent the program off to be run. And so we're not going to run that again, because it would take ages again. So we're instead going to run these two functions, which extract the information to get the bits, and then which turn those bits into text. And then we can take a look at what this new piece of text is. So there you go. It looks pretty similar to what we had earlier, which is good because it should look exactly the same. Now we can go and run it and see what happens. We have to stop what we were running before, run this new version, and we have an error. Now, of course, we have an error because it's not using new lines, but it's got these delimited in to make the new lines. So the easiest way around that is for me just to print this rather than have the Jupyter Notebook do it automatically. So that was a mistake in the human interface rather than in the quantum computer. Now let's run this, and there we go. It is a game that is running and which was stored on a quantum computer. We don't really have to go any further than that in the game. That's it. We did what we intended to do. So just to make sure that this actually was something weird, this actually did go via a quantum computer and we didn't accidentally run it on the simulator. Let's do job.results and then brackets and then get and then underscore counts and do this for one of the circuits. So let's do it for the first circuit, blah, 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 blah. I think that's good. You can have a look at that. And you see that it is indeed a horrible noisy output that we can expect from an actual quantum computer. So yeah, we did it. We stored a game in a quantum computer. We got it back out. It played. I mean, what more is there to say? It was a fairly pointless endeavor. We did it. And now it is done. Enjoy the rest of your day.